Right, so again, very similar thing. Question number 2, a little bit of inorganic. So X is a p block element in periodic table. So you know what are the p block elements. It exists as a diatomic gas. So I have like Cl2, the halogens, which can be halides, fluorines, F2 maybe, chlorine, chlorine, then fluorine, chlorine, and there is nitrogen, there is oxygen, all are diatomic. I cannot go for bromine because it is a liquid. Iodine, sometimes you cannot go because it is a solid. So what else we have like diatomic p block elements? So we'll see. X exhibits a wide range of oxidation states. So typically these have wide range, except the fact of fluorine and oxygen is a little bit not wide range actually, but they also have. And Y dissolves, no, Y is the most common hydride of X. Okay, so if you think about this hydride, for an example, for chlorine, so it gives you HCl. So nitrogen, the common hydride is ammonia. And oxygen, it is water. And here it is HF, for an example, right? And they say Y dissolve readily in water to give a basic solution. So you see here all these are, this is neutral, but these two acidic, so it should be this one, which gives a basic solution. So you automatically find Y is ammonia. And you find X is nitrogen. You have found it. And Y acts as an oxidizing agent? Yes, reducing agent. So we have seen the reducing and oxidizing activity of this ammonia, I think, in the beginning of our discussion. I think it was in 2011. And sometimes it acts as an acid, yes, and a base. So we have all seen these characters of this. The diatomic gas X is used in the manufacture of Y. So typically, you know, nitrogen is used for the production of ammonia through the Haber process, right? So identify X and Y. So X is nitrogen and Y is ammonia. The diatomic gas X is generally considered as inert. So briefly explain. So you have to explain why it is generally considered as an inert. So you have to explain there is a triple bond in between the two nitrogen atoms, right? So the bond dissociation enthalpy is very, very high. So that if you want to make it react, you have to give a higher energy to break the bond. So therefore, it is very, very inert. Okay, so that is a normal explanation that you can give. And then write the chemical formula of 3 oxides of X. So we have already seen this. So you can write down nitrous oxide, nitric oxide, nitrogen dioxide, and nitrogen trioxide or nitrogen hexoxide, and even nitrogen pentoxide. So these all have different oxidation states, right? +1, +2, +4, +3, +5. So you have to mention the oxidation states as well. Right, so in each of the following instances, it gives a balanced chemical equation to indicate the action of Y. So Y as an oxidizing agent. So this means Y oxidizes something, okay? So can you remember about reaction that Y, which is our ammonia, for an example, with something that is going to be oxidized? What do you think? Can you think about the reaction with sodium with ammonia, if you remember? So sodium with ammonia, it gives you NaNH2 and will liberate hydrogen, right? So you see here, there can be many other reactions that you can, even with lithium or even with magnesium. So with lithium, it will be lithium nitride and hydrogen. So it will be a different reaction. So you see here, sodium is 0 here, but sodium here is +1. So you see here, sodium is oxidized. So that is why it acts as an oxidizing agent. In the similar way, you can think about ammonia reaction. You can give the states if you like, okay? And this is also gas. And even this can be aqueous solution. So this could be an aqueous solution. And think about ammonia reacting with, for an example, chlorine. So we have seen this reaction many times, and we have predicted the products of this particular reaction many times. And we said at different conditions. So there can be different products, for an example. So this gives you nitrogen and HCl at some case, or it can be given like nitrogen plus ammonium chloride. So in some other cases, it gives nitrogen plus ammonium chloride, right? So these are the two main reactions that come across to my mind. Or even, in some cases, this could give even NCl3. If I can remember, NCl3 and HCl. So this is also possible when ammonia reacts with chlorine. So you see here different products at different conditions. So trying to elaborate more, like, to be honest, what exact condition this is obtained, like nitrogen with HCl, and what exact condition with nitrogen with ammonium chloride, and what exact condition with NCl3 and HCl. So we have discussed this. So if you do not remember, so please go through this again and keep it in your mind. Okay, so these are some basic reactions that you can think of writing, or even you can write down the general one part of the process of the production of nitric acid, like ammonia reacting with oxygen, forming nitric oxide, NO. So that is also possible. You can write that one. The important part is not only writing, you have to balance as well. Okay, so when you write simple reaction, it is very easy to balance. So don't go for complex reaction when it is still balanced also. So that's it. So yeah, and a separate question now. So consider the hydrides of the elements in group 2X which belong, okay, which are analogous to Y. So Y is NH3 ammonia. So below we have PH3, and then we have ASH3 arsenic, and then have antimony, SbH3. So for an example, we'll compare this. Sketch of variation in the boiling points of these hydrides, including Y, in the graph below. And in your sketch, indicate the hydrides using the chemical formula. Values of boiling points are not required. So this is theory. When you go down from phosphorus to for STBM, for an example, antimony, so it should generally increase like this. So it should be going like this, right? So here you can think about phosphorus, arsenic hydride, and SbH3 for an example. Okay, and PH3 here. And this is basically because of the increase in molecular weight that boiling point increases. So when you think about the other factors, so nitrogen should come here because of this low molecular weight. But the point is nitrogen is a little bit higher. That is very important to understand. Nitrogen is a little bit higher than PH3. And it is a little bit less than this ASH3. So don't forget. So NH3 is a little bit higher, right? The main reason for this is you don't see hydrogen bonding here in PH3 or ASH3 or SbH3. It is ASH3 is higher, still higher than ammonia because of the molecular weights, but it is higher than PH3 because of the hydrogen bonds present in NH3. That is the major reason. Give reason for the variation in boiling points in part 5 above. Okay, so they have also asked the reason. So the first reason that you have to mention here, in general, when the molecular weight increases, the boiling point increases. That is why the boiling point increases from PH3 to SH3 to SPH3. But nitrogen in ammonia. Additionally, they have hydrogen bonds. That is why the boiling point of ammonia is higher than, even higher than pH 3. Okay, so you can mention that clearly. Right, but you would observe when an aqueous solution of Y is added to a solution of aluminium sulfate. So basically, an aqueous solution of ammonia is typically will form ammonium hydroxide, right? So it's like mixing ammonium hydroxide with aluminium sulfate, right? So it's like this. So when you mix these two, aluminium is going to combine with this hydroxide, and it will form the gelatinous white color precipitate, which is called aluminium hydroxide. So what is the observation? They're asking the observation. So you can write down a white color gelatinous precipitate is observed. Write the chemical formula of the species that give rise to the observation. So it is aluminium hydroxide, AlOH thrice. We give one chemical test to identify Y. So identify Y means it's ammonia, right? So ammonia is Y. So you can write down the Nessler's reagent. So by using Nessler's reagent, so you can identify using Nessler's reagent. So when you trying to identify using Nessler's reagent, you can observe brownish color, right? That is one method. The other method is you can use even HCl vapor. So when you add HCl vapor to ammonia, so it will form NO4Cl, giving a white color vapor. So this will give white color vapor. Okay, white color vapor. So these two are very, very specific tests. Or even you can write very, very simply like using litmus paper, right? So you can write what is happening when you use a red one. The basic can change into a blue color. So there is a basic one. So don't go for this one. I would recommend to go for Nessler's one because there is only one. If not, you can go with this one or even this one. So no problem in that. You just need to identify what you are writing. Okay. Right, so Z is an oxo acid of X, and it's a strong oxidizing agent. So what are the oxo acids of X? So you're asking about nitrogen. So there is HNO2 typically, and we have HNO3, the oxo acids of nitrogen. These two are the typical ones. This is a little bit of unstable, but this is very stable. And it's a strong oxidizing agent. So when you have these strong oxidized agents, automatically this is cancelled. So they are talking about HNO3, right? So this is the one. State the products obtained when hot concentrated Ez reacts with sulfur. So Ez is HNO3. So you have to write down this reaction. HNO3 plus sulfur. Even you don't have to write down the reaction because they only ask for the products. So you need to just write down the product. So sulfur with HNO3, since this is a very, very strong oxidizing agent, the sulfur will be automatically converted to H2SO4. That is one of the product that you can expect here. And the other product is from NO3. So it will be NO2. And finally, water. Okay, so you just need to write down these three products. You don't have to even write down this equation, right? So yeah, so that is it. So that is about this nitrogen and this ammonia and this oxo acids and all those things. Okay, so this is a typical question. So identifying the element is very, very basic here. You can automatically identify the element here based on the information given. But you see here, you should know some reactions of nitrogen here, and you should know some periodic properties, and here some reactions again. So it is very important to understand the importance of knowing some reactions in inorganic chemistry. Okay. So that is part A done. So we have to move to part B here. So it gives A and B are compounds of two p block elements. that belongs to the same group. Okay, so again, p block element, and now here it's two elements A and B which belongs to the same group. Okay, but we don't know whether they are consecutive, like adjacent in the same group or not. A exists as a colorless, okay, odorless liquid at room temperature. So A exists as a colorless and odorless. So what do you think about that? Okay, so what are the liquids? So we have bromine liquid there. So yeah, it can be bromine. Or for an example, okay, so this bromine is from the element, but they are talking about compounds. So we have to elaborate more, right? Room temperature and atmospheric pressure. It is also found in the gaseous and the solid form. Okay, so this gives you the idea of some element that is present in the room temperature and pressure, in the solid, in the liquid, and in the gaseous state. And surely it should be water. Okay, so it should be originated from oxygen. So what are the other elements there in oxygen group? Oxygen, sulfur, then selenium, tellurium, polonium. Okay, this is sulfur. So the rest can be one of these, so we will check. The solid state of A is less than that, so they are talking about the ice. Okay, ionic and polar compounds are readily soluble in A, so completely confirm this is water. B is a colorless gas at room temperature. Okay, so B is a colorless gas, so it can be yeah, like SO2, because these are more towards like solid form, so it can be sulfur compound. A filter paper moist with the lead acetate turns the black on. Okay, so this gives you the confirmation. So normally when you have lead acetate, like this lead acetate, for an example, lead acetate with H2S. So this is, there is no hydrogen here, sorry for that, because that is why there is lead here. So this will be 2 with H2S, so it will form PBS, lead sulfide, which is the black color precipitate, plus and this hydrogen combined with these acetate ions to form 2 acetic acid. So this is the normal reaction with lead acetate, right? So it should be H2S. So it's again a hydride, right? So oxygen, water, and H2S. So they are telling identify A and B. So A is water, B is H2S. Sketch the shapes of A and B showing lone pairs of electrons where necessary. So you can show here oxygen, hydrogen, and oxygen. There are 2 lone pairs. And this one, and sulfur. So you can, sorry for this will be hydrogen, and you can show this lone pairs also. Okay, lone pairs on electrons. So you see here there is 2 lone electrons, 2 lone electrons. But if you wish, like for an example, now if you think of these 2, oxygen is more electronegative, right? So the best way to show this is since oxygen is more electronegative, so you can show here the bond angle of this oxygen to hydrogen a little bit larger, like little bit of larger bond angle than H2S. That is one, that is a good practice actually. Okay, so don't forget about that. Giving reason, state whether A or B has the larger. Okay, so they have asked which one has the larger bond angle. So what do you think? So you have to give reason. So I have already told which one has the largest bond angle. So this one has a higher bond angle than this one. So why is the reason? You can tell oxygen is more electronegative than sulfur. So these bonding electrons are more concentrated around the oxygen atom, making repulsions more and more, right? Give me a second. So you can mention the bonding electrons are more concentrated surrounding the oxygen atom. So there will be more lone pair, bond pair repulsions than in H2S, here in water, in H2O. Therefore, the bond angle is higher. Okay, so you can mention that. In each of the following instances, give a balanced chemical equation to indicate the action of A. So A acts as an acid. So what is A here? So A is water. So think about a place where A acts as an acid. So A acts as an acid means, so A react with something, and that something will like accept this H plus from water. That is what it is, an acid, right? So the common example is it's reacting with ammonia because it will be in equilibrium. So there will be NH4 plus. So ammonia will be the base that take the H plus from water, and OH minus is one. And A as a base, so it is again very common. So H2O reacting with the acid, the reverse. Because in the acid, so you see here, you have acetic acid. So again, this will be an equilibrium. So this one, acetic acid will give H plus and it will be taken by water. So water here act as a base, taking this H plus from acetic acid. So here there will be H3O plus forming and acetate on it. Okay. You don't have to worry about the physical states here because it is an organic chemistry question. But it is better if you write the physical states as much as possible as you wish for, because it's very good. Make your answer complete. Write the balanced chemical equation for the reaction of B with aqueous lead acetate. So it is given here. I wrote this one. So lead acetate with H2S. So PBS, the black precipitate, and 2 acetic acid is formed. There is this. Write what you would observe when A and B are added separately to an acidified solution of BiCl3. So write down the balanced chemical equations as well. So basically, when you add excess A, so BiCl3 with, I would say, first we will go with A here, which means water. So if you remember about BiCl3 and SbCl3, both of them been in the acidic medium. First we add HCl, so BiCl3 and SbCl3 is forming. Then when you dilute the solution, because the solution is still acidic, and when you dilute the solution, you will observe white color precipitate. So the observation here is a white color precipitate, and the reason for this white color precipitate is BiOCl. Okay, so this will be BiOCl, which is going to be your white color precipitate, and HCl is given out. So this is one reaction. And the second, the observation here is forming a white color precipitate, right? So that is one. The second thing is you are going to add BiCl3. So don't forget, here they are given acidified. Then you add H2S. So what is going to form? So Bi2S3. So if you remember, this is a group 2 precipitate. So you can remember, if you remember, this is a black color group 2 precipitate. So you will right here, a black color precipitation is observed, right? So black color. So again, HCl is given out. But don't forget, you have to again balance the equation. So it will be very easy balancing here. So don't worry about that much. So you can do that. here you have to just put 2 here. So H2 and Cl is balanced, 3Cl, Bi, and oxygen is balanced. And here, so 2Bi, so I will put 2 here and 3As, so I can put here 3, and to balance hydrogen, I just need to put 6 here. So chlorine is also balanced. So this is a very simple balancing. And this summarizes our discussion on this second question as well. So you see here, there is a little bit of reaction that you need to know here. So I told you before, now everything will be within your theory syllabus. So more or less you can get full marks if you know your theory really well.